So the title of my talk is Stellar Population and Ionized Gas in Central Spheroidal Galaxies. And I divide the presentation in introduction, where I talk briefly about cluster of galaxies, central galaxies, and about two mechanisms that can affect of how these galaxies evolve, that are cooling flow and agent feedback. After that, I will present the objectives of this work, methodology, results, and finally some conclusions. So, a cluster of galaxies are the largest gravitationally structures in the universe, and they are composed of three components: dark matter, intracluster medium, ICM, and galaxies. So the dark matter are distributed in an extensive halo and is the most important component in terms of mass. About 80% of the mass of clusters are in the form of dark matter. And intracluster medium corresponds at 15% of cluster's mass. And ICM gas is hot, dense, and also emits in X-rays due to Bremsstrahlung process. And finally, galaxies with only 5% of the total mass of the clusters, and they can be divided in two categories: central galaxies and satellite galaxies. And in this work, we will focus on central galaxies. So, these galaxies are generally elliptical galaxies. And if you note in this figure, we have a cluster of galaxies, and here in the center, we have an elliptical galaxy. And if you note, this central galaxy is bigger and brighter than the others in the cluster. Beyond that, they have some distinct properties of non-central spheroidal galaxies with comparable mass. Like they have higher alpha-2 ion ratio, and they have more probability to be a radial galaxy, etc. And how these galaxies are in a privileged location in the cluster, these objects suffer different process from those that are not central, like the cooling flow and the agent feedback that we will be studying this work. So, the cooling flow is a process when the ICM gas in the cluster lose the most of its pressure and thermal energy by emission of this of the X-rays, and this happens quickly. The results be a large cooling flow that falls into the central galaxy, and this cooling, predicted in this way, would cause intense star formation, which is not observed. So what suggests that the medium is reheated by some source. And a mechanism capable to explain this reheating is the nuclear activity, common in central galaxies. This activity, or AGN, is when the black hole is accreting matter in the galaxy. In this process, the redeposition of energy and momentum into the interstellar medium of galaxy through the outflows and radiation is called agent feedback. This feedback provides enough energy to prevent the gas from cooling, and in the central regions, extinguishing the formation of stars. So, it's common for central galaxies, like I said before, to be radial galaxies. So these galaxies are characterized by jets with strong radio emission. So if you note in this figure, we have a combination of these three images here in the right side. So in top panel, we have the X-ray image. In the middle, in visible range. My dogs are crazy here, sorry. And the bottom panel, we have the radio range. And if you note here in the X-ray image in the top panel, we can see how these jets are powerful. Here in these dark concavities here, we have these dark bubbles here are produced by the jets. So here in blue we have the ICM gas, so they are affected by the jets. So we want to understand how some physical properties influences the formation and evolution of central galaxies. So we will investigate the stellar population properties and the ionized gas of a sample of central galaxies extracted from the spider catalog in function of both the halo mass and the stellar mass of the galaxy, to obtain information that allow us in the future to set up a scenario for the formation and evolution of these galaxies. So, to obtain information about the stellar population, we combine the optical spectra of the Sloan survey in halo mass and velocity dispersion beams, totaling a sample of about 15,000 central galaxies in 71 beams. So here we have the number of galaxy per beam of halo mass here in the horizontal line, and the dispersion, the velocity dispersion here in the vertical lines. So all these numbers after that are number of galaxies. So, and we use the starlight code to obtain stellar population information, like mean stellar age and metallicity, extinction, and the power law associated to AGN. And to make the starlight synthesis, we use two templates of simple stellar populations that are Brusol and Charlot and Vazdex. But how Vazdex shows a better correlation, I will use only this base in this presentation. So here we have a figure, an example of how starlight reproduce our observed spectra. Here in blue, we have the model produced by the starlight, and in black, we have the observed spectra. And finally, to identify the presence of ionized gas, we measure the equivalent width of H alpha by Gaussian fits. Here in orange, we have the Gaussian fits. In blue, the observed spectra, and the dashed lines indicates the center of the spectral lines. Okay, now I can present some results. Here I have 4 graphical relations between physical properties.
2 minutes.
Age, metallicity, extinction, and the power law as a function of the halo mass and velocity dispersion. So here in the graph that indicates age, I don't know if you can see my cursor. The color represents the property, so the age, and the vertical axis represents the halo mass, and the horizontal represents the velocity dispersion. So we can see some correlations here. So the age increase with the growth with the velocity dispersion, and decrease with the growth of the halo mass. Metallicity represents the behavior where the metallicity decreases with decrease of velocity dispersion and also halo mass. And extinction and power law presents the same behavior, so they become lower for higher velocity dispersion and for higher halo mass. And the same behavior are present here in the equivalent width of H alpha. So these 3 properties, extinction, power law, and equivalent width, have the same behavior. And I present here some numbers that are correlations of these graphs. And we can see more clearly here these correlations. So look, for A that are positive for age and metallicity here, indicating that the age and metallicity increase with this property, so the velocity dispersion, and the other ones are negative in the same regime, so they decrease in for higher velocity dispersion, they decrease. For halo mass, we have negative only for age and positive for others. And after that, we want to describe our coefficients in a physical theoretical model involving the cooling flow and age and feedback. But only next talk, because I don't have more time. So I can make some conclusions with this. So we find that extinction, the equivalent width of H alpha, and the contribution of a power law increase as the halo mass increases, and the velocity dispersion of the central galaxies decreases. The H have the opposite behavior, become lower in the same regimes, and the metallicity is higher as halo mass and velocity dispersion increase. So these relations are quite sensitive to the basis that I use in the synthesis, and we'll talk more about this and about these conclusions in the next talk. So thank you.
Okay, thank you. Obrigado. Perguntas?